this video, we're going to talk about how to find impulse from non-constant forces. So impulse, J, capital J, right, is defined as the change in momentum. And these are vectors. And change in momentum of a single object. And so we saw how then that also is going to relate to the force and the time. So we know that then J is equal to the change in momentum, which then is equal to the average force that something experiences over some amount of time. So the total average force that something experiences times the time in which the object experiences that average force. So I push on something, and the longer I push, the bigger the change in momentum, right? But what if instead of just looking at the average force, say during some time, we want to look at actual force that varies as a function of time and is applied for some time. So I start pushing on something, I don't push very hard, and then I push harder and harder and harder, and then how does that change the momentum as a function of time? So what we have then is the equation that the impulse would then be given by the continuous version of this, which would be the integral of f dt. So again, dt is just a tiny little time, and so then the force, which depends on time, then would vary with time, and you just add up all the little change in momentums, all the little impulses from each bit, and that gives you your total impulse and therefore your change in momentum. Now, so really it's just basically here that you would have this equation for finding the impulse. But what you need is to have a force that varies with time to do this. Note that that is very different than what we saw with work, right? So I'm going to put here in contrast, oops, and I just realized this should have a vector over the force, of course, that for work, which was a scalar, so work was our change in kinetic energy. So I'll say here in contrast, that was given as f sub x or f dot dr if we do the general form of it. Either way, this was going to be force that varies with position. So you have to be very careful with a function in a problem. If you're given a force as a function of time, then you're going to use impulse. So force that varies with time would be our impulse equation, and a force that varies with position would be the work kinetic energy theorem. So keeping that straight is important. All right, so once we have then seen that we can have this form for the variable force, then really all a matter of it is to just apply that. So if you're given a force as a function of time, for example, let's just take a t cubed, then you would have to be, told that what time interval over this force acts. Then you can get the change in momentum of the object. So you would just have here the change in momentum, J, which is the impulse. So that'd be mv final minus mv initial would equal the integral of f sub t dt. So a t cubed dt evaluated from t initial to t final. So then it just becomes a calculus problem. But the key here and the thing to keep track of is that you need to have a force that varies with time to use the impulse momentum relationship. And that this applies to a single object. So this is going to matter a lot when we get to the next module. That we see here, this is the change in momentum of a single object of mass m, and this is the force on mass m, then integrated over time. So you apply a force to a single object and do that over some amount of time. That changes the momentum of that single object. So it's a single object, and it's very different than work in that you are dealing with force as a function of time again. Okay, let me know if you have any questions.